This lesson is about logarithmic functions. And logarithmic functions are an extremely useful type of function that are often misunderstood by students when first learning them. My advice is to try and learn the algebra involved with logarithms first, and then later on try to learn how they are applied to different situations. The algebra involved is really what you're being tested on in this class, and it's really not that difficult to catch on to the algebra, though it does look very strange. So try and learn that first, and then work on the applications. Logarithms were first developed in the 17th century by the mathematician John Napier. At the time, they were used as a means to simplify calculations involving multiplication of values involving many significant figures. However, in the 18th century, the mathematician Leonard Euler discovered their usefulness as the inverse of exponential functions. Since calculators now perform multiplication of many decimals very easily, the former use is now antiquated. Our study will focus on the latter use, defining logarithms as the inverse of exponential functions. We saw in the last section that an exponential function is a one-to-one function, and because of this we know that these functions must possess an inverse, because all one-to-one functions have an inverse function. But to discover what that inverse is, we would need to start off with an exponential function, and then swap the x and the y values, which would result in x equals b to the y. The problem with this is that we don't have any algebraic means of solving for y. So we go to making a new definition. For all real numbers y and all positive integers b and x with b greater than 1, y equals log base b of x if and only if x equals b to the y. So we're basically coming up with a new function called the logarithm, and we're going to talk about what it means as we go through this lesson. But we come up with a new function called the logarithm, which is just defined to be the inverse of an exponential function, where b is called the base of the logarithm, x is called the argument of the logarithm, y is called the result of the logarithm, which is an exponent. So log base b is the exponent to which the base b must be raised in order to obtain x. So kind of keep that sentence in mind. It will help you understand as we go through the next few slides here. Now, the first thing we want to learn is how to convert between exponential and logarithmic form. So using the rule y equals log base b of x, if and only if x equals b to the y, we can see how to convert an equation between exponential form and logarithmic form. This is one of the most important topics we learn when working with logarithms, just switching between exponential and logarithmic form. There's a lot of equations that you can solve just from switching from one form to the next. So make sure you really are confident in this skill. So we're going to do some examples, and we'll just start with some equations in logarithmic form, and we're going to convert them into exponential form. So the base of your logarithm is the base of your exponential equation. Now keep in mind your exponential equation would look like x equals b to the y. So the base is very easy to identify. That's where I always start. So the base of my exponential equation is 3. The exponent on that base, that is the result of the logarithm. The logarithm is an exponent, so this 4, the result of your logarithm, is the exponent here. And that's equal to your argument. Now this might make a little bit more sense in exponential form. 3 to the 4th power, if you multiply 3 4 times, it will in fact equal 81. So this statement as a logarithm, log base 3 of 81 equals 4, it's a true statement, it's a valid statement, but it might make a little more sense in exponential form. Switching between those two forms is an essential skill. So let's try another. Log base 4 of 4 equals 1. So the base is 4. All right, that's coming from that number right there. The exponent is 4. So the exponent is 1. So 4 to the first power is equal to 4, that argument. So 4 to the first power is equal to 4. And that is something that we know as an exponential form. Next we have log base 2 of 64 equals 6. So I take my base 2, raise it to the 6th power, and that gives me 64. That's an equivalent statement as an exponential function. This looks a little bit more strange, but follow the exact same rubric and it'll make perfect sense. So the base is 3, 1/2 is my exponent, and that's going to be equal to the argument. And based off of what we know about rational exponents, 3 to the 1/2 power is in fact the square root of 3. All right, next up, log base 7 of 1/49 equals -2. Again, it looks a little strange, but let's see what it looks like in exponential form. So it would be the base 7 raised to the exponent -2 equals 1/49. And if you recall how negative exponents are evaluated, a negative exponent is evaluated by making it positive but moving it into the denominator. So 7 to the -2 is in fact 1/49. So this is a true statement. The last example of these, log base 1/2 of 1/8 equals 3. So the base is 1/2, the exponent is 3, and the argument is 1/8, so that's equal to 1/8. And this works out as well because when you evaluate 1/2 to the 3rd power, you take the numerator and denominator separately to the 3rd power. 1 to the 3rd is 1, 2 to the 3rd is 8. So it checks out as well. Similarly, converting from an exponential form into logarithmic form is just as important, but it's just as easy. Let's try it. So if I have 3 to the 4th power equals 81, to change this into logarithmic form, it's currently in the form x equals b to the y. And I'm going to switch it into the form log base b of x equals y. So I just use that as kind of a road map, basically. Again, the base is easy to see. So I say log base 3, and the argument of the logarithm is going to be the 81, the number on the opposite side of that equal sign. Because remember, the result of a logarithm is an exponent. So this number on this other side is going to be the 4, which is the exponent in the exponential equation. So you just kind of have to remember how to change that over and get used to it because it's really an essential skill. Okay, here the base of the exponent is 9. So log base 9. That's easy. The exponent itself is 3/2. That's an easy one to do too, as long as you remember that the result of a logarithm is an exponent. And that just leaves the argument, which has to be the 27 in this case. Okay, 25 to the 1/2 power equals 5. So to work this through, the base here is 25. So I'll put my 25 in. The exponent is 1/2. So I'll write that in. And that leaves the 5 as the argument. So log base 25 of 5 is equal to 1/2. Now these statements still may seem strange to you, and that's perfectly fine. If they happen to still seem strange, then as you work through examples and see how we solve problems, for instance, they'll start making a little bit more sense. But again, like I said earlier, if all you remember here is all you learn here is how to do the algebra of logarithms, that's perfectly fine. That's a great introduction to logarithms, is learning the algebra involved. If later on in another math class you start seeing applications, I have no issue with that whatsoever. So, log, for part D, the base is x, and the exponent is negative y. And that leaves the argument to be the z. So I'm just following the same general roadmap that I've been calling it each time here. Okay, for part E, 7 to the negative second equals 1 over 49. So my base is 7. That's the part that has the exponent on it. The exponent is negative 2, which leaves 1/49 to be the argument. So the log base 7 of 1/49 equals negative 2. And this one's a little bit strange, but I put it in here on purpose. When you start using the calculator to do logarithms, you'll see where this is coming from. But for now, just follow in the motions. And in case you aren't sure, this symbol right here, the sort of an equals, but you have a wavy, they're a little bit more wavier. That means approximately. So 10 to the 0.4771 isn't exactly 3, but it's really close to 3, is basically what that says. But I'm going to write this in as log base 10. And the argument is going to be the 3. Log base 10 of 3 is going to be approximately that exponent 0.4771. When we do applications with calculator later on, you'll see what's happening there. All right, solving basic logarithmic equations. So now what we're going to do is take our knowledge of how to switch between logarithmic and exponential form and see how we can use that to solve basic equations. Now, if I have this, log base 4 of x equals 3, so I want to figure out what x would have to be. Maybe it doesn't make so much sense in logarithmic form. That's okay. It might make more sense in exponential form. So let's just switch it over to exponential form. So the base is 4, the exponent is 3, and the result of that would be x. Well, now I just need to solve for x, and that's pretty simple to do. I just need to take 4 to the third power. And if you don't know it, that's okay. Use your calculator. 4 to the third power is 64. So what that would mean is the log base 4 of 64 is equal to 3. So we've solved that equation. And solving these equations by changing them from logarithmic form into exponential form, or the other way around, so from exponential into logarithmic form, that's a great strategy. Okay, so log base 6 of x equals 3. So what this would look like as an exponential equation, 6 to the third power equals x. Well, again, 6 to the third might not be something you know right off the top of your head, but if you grab the calculator, you'll find that it is 216. So this means that the log base 6 of 216 is equal to 3. Next up, log base x of 125 is equal to 3. In exponential form, this would look like x is my base, 3 is my exponent, so x to the third is equal to 125. Okay, so a little bit more complex to solve here, but still not too bad. Notice that 125 is a perfect third. It's 5 to the third power. And so I have a situation where I have an exponential, two exponential pieces that are equal to one another. The exponents are the same. We used a rule in the last section to solve this. If the bases were the same, that meant the exponents were the same. Now we can use the same thing because it's also true that if the exponents are the same, that the bases are also the same. So that means log base 5 of 125 is equal to 3. Or equivalently, 5 to the third power is 125. Okay, log base 9 of x equals 3 halves. So I need to change this into exponential form. See what that looks like. So the base is 9. 3 halves is the exponent, and that's equal to x. Okay, 9 to the 3 halves power. In order to figure out 9 to the 3 halves power, just remember that you can do this as 9 to the third power, then to the 1/2. Okay, so that's just 9 to the third and then taking the square root. Or you can do 9 to the 1/2 raised to the third. Either one of those is equivalent because 1/2 times 3 is still 3 halves. I prefer this second method because when I take 9 to the 1/2 power, that's just 3, which is a small number, and then I raise 3 to the third, which is 27. So the result of this is 27. If you did the other way, if you take 9 to the third and then the square root of that, that's fine. You're just working with bigger numbers, that's all. Okay, log base x of 6 equals 1/3. So x to the 1/3 power is equal to 6. So how do we go about solving this? Well, we're trying to figure out something that when we take the cube root of it, we end up with 6. So in order to do the opposite of that, to get x by itself, we need to cube both sides of this equation. 3 times 1/3 is just 1, so that makes x to the first power, or just x. 6 to the third is 216. So that says the log base 216 of 6 is equal to 1/3. And the last one's a little bit of a challenge, but still works out in the same manner. I'll work it through here with you. X to the 3/4 power is equal to 27. So what I'm going to do is split it up in the same way that I did the last problem. What I'm going to do first is take the cube root of both sides. All right, so when you take the cube root, you're raising things to the 1/3 power. Now, 3/4 times 1/3, the 3's cancel out and leaves me with 1/4. So this becomes x to the 1/4 power, which is still not simple, but it's less complex than the 3/4 power. 27 to the 1/3 is just the cube root of 27, which is 3. Now to get x by itself, I need to multiply or raise both sides to the 4th power, because 4 times a 4th is just 1, so I have x by itself, and 3 to the 4th is 81. And there we have that done. Let's take a look at how we go about evaluating some logarithms. without the use of a calculator. So if I wanted to figure out, for instance, log base 2 of 16. To do this without a calculator, basically you want to change it into an exponential function. That's when it comes to solving logarithms, you almost always want to be thinking that in your head, to change things into exponentials in order to move forward. So if I say the log base 2 of 16 is equal to x, some unknown value, I can change it to an exponential by coming up with a base of 2, the exponent is x, equals 16. So 2 to the x equals 2 to the 4th power, which means x is equal to 4. So log base 2 of 16 is equal to 4. So you're basically asking, what exponent do I need to raise the base 2 to in order to get 16? So if you think about it in that way, you might not even need to go through many other steps. So let's try it here. What do I need to raise 27 to in order to get 3? Well, 27 to the 1/3 power would be 3. So I think the answer here is 1/3. But I'm going to check it. So 27 to some unknown exponent would be 3. So let's see what happens. So 27 to the x would be 3 cubed to the x. I've got my bases the same. So 3 to the 3x equals 3. We can think of that as 3 to the 1st power. So now I have the bases the same, so that means the exponents are the same. So x equals 1/3. So it works out. So you can think of these in those kind of terms. It might make it a little bit simpler. So log base 3 of 243. So what exponent do I need to raise 3 to in order to get 243? Well, I know that 3 to the 5th power is 243, so that exponent is 5. And you can check. If you rewrite 243 as 3 to the 5th power, that implies x equals 5. Log base 10 of 100,000. Well, 10 to what exponent is going to be 100,000? Well, let me go ahead and change this over to something that's useful. So I know 100,000 would be the same thing as 10 to the 5th power. So that means x equals 5, or the result of that logarithm is 5. Log base 4 of 2. So what exponent do I need to raise 4 to in order to get 2? So 4, the square root of 4 is 2, so 4 to the 1/2 power. Log base 10 of 0.0001. Well, what exponent do I need to raise the base 10 to get 0.0001, which I know is also expressible as 10 to the negative 4th power? Well, that means it's negative 4. So log base 10 of 0.0001 is negative 4. And as we get into the calculator, these things can be a little bit easier to do, but I'm just trying to show you that you can use these properties in order to solve them without the calculator to start with. All right, so next up, properties of logarithms. We had a lot of properties of exponentials, and we have similar properties of logarithms. So let's begin. The first is that a log base b of 1 is equal to 0. So a log of any base of 1 is 0, which might not make a whole lot of sense in the way it's written, but if you change it into exponential form, a base b to the 0th power is equal to 1. it's just a restatement of that exact same property from exponentials. In fact, almost all of these are. Log base b of b is equal to 1. That's just a restatement of the principle. The base b raised to the first power is equal to b. So, restatement of something from exponentials. Log base b of b to the x is equal to x. Well, this is a little bit trickier, but you can actually change this over. Your base is b. The exponent would be this x over here. And then that's equal to the argument, and the argument is b to the x. So it's something that, it's a property that doesn't get used very often, but it is, when it can be used, it's very helpful. Similarly, number 4 here, b to the log base b of x is equal to x, which, again, it's similar to number 3 in that it's a trivial statement, and if you change it in an exponential form, because, I'm sorry, if you would change it into logarithmic form. So it's in exponential form right now. So log, your base would be b, that would be your base right there. The argument would be x, and the exponent is log base b of x. So it's kind of trivial if you switch it over this way. But it's a property that doesn't get used often, but when it does get used, it is very helpful. Okay, here's one that does get used quite a bit. Log base b of x times y is equal to log base b of x plus log base b of y. It's a similar statement. In fact, it is the same statement in logarithmic form as a to the x plus y equals a to the x times a to the y. I'm not going to go through the proof of this, but just kind of understand that it's the exact same statement written in logarithmic form. Similarly, number 6, log base b of x divided by y is log base b of x minus log base b of y. So you can take, if you have a logarithm where the argument is divided, split it up into 2 separate logarithms that are subtracted. Or the other way around, you can combine as well. This is an interesting statement. If your logarithm has an argument that has an exponent, you can pull that exponent out front as a constant multiplier. So see where the r went over here, out front as a constant multiplier. Again, I'm going to state that without proof, and I'll show you how it's used algebraically in the coming slides. Lastly, log base b of x is equal to log base b of y if and only if x is equal to y. This is a restatement of that principle that we used with the exponential functions that we used to solve equations. And same thing here, we're going to use it to solve equations. Okay, using some of those properties that we just saw, we're going to do a couple of very common problems with logarithms. One being to combine logarithms into a single statement, and the other being to expand them into multiple logarithms. So let's start with a statement like this: 2 log base a of x minus 3 log base a of y. And let's say we want to combine this into a single logarithm. So we just use those properties, and generally it's the properties, the 3 properties involving the sum of 2 logarithms, the difference of 2 logarithms, and the exponent rule that kind of come into play. So the exponent rule here, if I have a constant multiplier of 2, I can make that an exponent on my argument. So I could write this as log base a of x squared. Similarly, I can do the same with the 3. I can just make it an exponent on my argument here. Log base a of y cubed. So I'm really just learning the algebra involved with these logarithms. If you're the type that wants to understand the details of what's happening here, I urge you to just learn the motions for right now, and later on work on trying to understand them. But for right now, just get the algebra down. That's all we're really looking for here. So I have two logarithms of the same base that are subtracted. I can combine them into a single logarithm if I divide their arguments. And you kind of have to follow the order of operations here. We couldn't have combined them into a single logarithm to start with because of those multipliers out front. We need to take care of the multipliers and then do the add and subtract rule. Okay, another example. Log base b of x plus log base b of y minus log base b of z. So the first two, I have two logarithms that are added. I can combine those into two logarithms whose arguments are multiplied, and then minus log base b of z. Next, I can combine these two into a single logarithm if I divide their arguments, because they are subtracted. So now I have one logarithm left, log base b of x times y divided by z. And that's all we need. Then next up here, 2 log base b of x minus 3 log base b of y plus 1/2 log base b of z. Start with the multipliers first, make them all exponents. So log base b of x squared minus log base b of y cubed plus log base b of z to the 1/2 power. Okay, the first two logarithms are subtracted, so I'm going to combine those through division. So it's going to be log base b of x squared over y cubed and plus log base b, and I'm going to change this into the square root of z. It's fine to leave it to the 1/2 power, but it's generally a little bit cleaner if you change it to a square root. So then log base b, these two are now added, so the square root of z is going to go in the numerator. So it's going to be x squared square root of z divided by y cubed. All right, and this last example that I have involves numbers. And so you might just end up with something you can simplify along the way a little bit more. So let's try it out, see what happens. Okay, log base 6 of 2 minus log base 6 of 4. We can combine those into a single logarithm by dividing their arguments. And over here I have 2 log base 6 of 3. So I can bring the 2 and make it an exponent on the argument. All right, so I can simplify a little bit here. I couldn't do that with these variables that were involved, but with the numbers I can. So 2/4 can be 1/2. 3 squared would be 9. Okay, and now the next thing is I can combine these two through division. So log base 6, and it's going to be 1/2 over 9. And to simplify that, maybe I'll come off to the side. So 1/2 divided by 9. We know we don't divide fractions. We just change it into multiplication by inverting the denominator. So this is 1/18. So it's going to be log base 6 of 1/18. And you'll run into questions that ask you to take it the other direction as well. So expanding logarithms. So you're given one logarithm and you need to make it into multiple logarithms. So for instance here, the x times y is divided by z. So I could split that up into two logarithms that are subtracted. So the numerator minus log base 2 of the denominator. And I can go further because the x times y could be split into two logarithms that are added. So log base 2 of x plus log base 2 of y minus log base 2 of z. And all the arguments of my logarithms are now linear. That's usually an indicator that you're done. So if I had any exponents on my arguments at this point, I should go ahead and change those to constant multipliers. So for instance, like this example, similar to the one we just did, but now there's exponents. So I'm going to change it into log base 3 of x squared y minus log base 3 of the square root of z to start with. Okay, which makes this able to split the x squared and the y into two logarithms that are added. So x squared plus log base 3 of y minus log base 3 of z to the 1/2, I'll write. And lastly, I just have these exponents to take care of. So I'll just pull the 2 out front. So 2 log base 3 of x plus log base 3 of y minus 1/2 log base 3 of z. And so all the arguments of the logarithms are now linear. So they're not squared or anything like that. So I know that I'm done. All right, one last example like this, log base b of x times y cubed raised to the 4th. So multiple ways we could do this. One way I'm thinking of is just go ahead and take care of that 4th power. So make it x to the 4th times y to the 3rd. Whoops, I'm sorry, y to the 12th, because you would multiply the 3 times the 4. Then you could split that up into two logarithms that are added. And now you have exponents on your arguments, so bring those out as constant multipliers. So 4 log base b of x plus 12 log base b of y. And that's as far as we can take that particular problem. Let's talk about graphing logarithms. Since we know that logarithms are the inverse of exponential functions, and inverse graphs are symmetric about the line y equals x, we can determine what the graph of a logarithm looks like using those facts. So we'll start with the exponential graph. We know what this is. Now, if I take the line y equals x, which would be along here basically, and I flip this graph along that line. So the point here at 0, 1 is going to flip and become the point 1, 0. And actually the asymptote is going to flip as well and become a vertical asymptote. And the rest of these points kind of fall into this sort of shape. So the green one there is the basic graph of my logarithm. And it's just based off of the inverse of the exponential. Its properties, first, the domain is from 0 to infinity. So you can only put positive non-zero numbers into a logarithm. Its range is negative infinity to positive infinity. It is 1 to 1. It always passes through the point 1, 0. So when we go to do any kind of graphing, we use this as our basic reference point similar to how we used the point 0, 1 with the exponential. It's an increasing function if b is greater than 1. It's decreasing if the base is between 0 and 1. There's a vertical asymptote at x equals 0. And shifts and translations all are going to work the same as before, but you need to start with the point 1, 0 since the graph doesn't pass through the origin. Stretching and shrinking, any kind of scaling, is more difficult because it's dependent on the base of the logarithm, so we neglect this in the class, similar to how we did with the exponentials. If you put a negative on the argument, so you put it on the inside of the logarithm, that's going to result in a horizontal flip, and a negative on the logarithm itself is going to result in a vertical flip. And if you ever want to find the domain of a logarithmic function, just set the argument greater than 0 and solve. So let's take a look at a few graphs. All right, so for instance, log base 4 of x minus 1 plus 3. So the first thing we need to do is figure out where our asymptote is going to be. And since it's a vertical asymptote, we want to look to the horizontal shift first. So the horizontal shift comes from this x minus 1. So I'm going to move to the right by 1 unit. So my asymptote is going to move to the right 1 unit. Now, this plus 3 is a vertical shift, and it's going to go up 3 units. So that point that would have been 1 unit in front of the vertical asymptote, which would have been right here, it gets moved up 3 units. So it gets moved up to here. And then I just draw in the basic shape of my logarithmic graph, which is, it kind of grows very slowly after that point, but it grows very rapidly toward that asymptote. Y equals negative log 2 of x minus 2. Okay, so here the argument x does not contain any horizontal shifts. So the asymptote is right where it was originally, at the y-axis. Normally there's a point, then 1 unit in front of there. But I have this minus 2, which is a vertical shift that's taking me down 2 units. So with that, that means that point is going to go down to right here. And because of that, I now need to take into consider one last piece. So this negative. So this negative is going to be a vertical flip. If it's a negative on the logarithm itself, it's a vertical flip. So normally my graph, would have grown slowly this direction and then very fast toward the asymptote, but it's going to be the opposite of that right now. It's going to switch that. So it's going to grow slowly this direction and very quickly up toward the asymptote here. Let's say we wanted to find the domain of these graphs. So the domain, I said, if you take the argument and set it greater than 0 and solve. So for instance, here I would get x is greater than 1. So that's the set starting from here, well actually from here, and going to positive infinity. So I'm not including the asymptote, but I'm including all the points after that. So that is my domain, and it's pretty easy to find with logarithms. Like I said, all you need to do is just take whatever your argument is, set it greater than 0. This was kind of trivial here because it's just x is greater than 0. There's not really anything to solve. But if you look where your function is defined, it tells you exactly where that domain is. Next up, y equals log base 3 of negative x plus 1. So there's no horizontal shifts here, so my asymptote is in the same place as usual. Everything is shifted up by 1 unit. So this point that normally would be here gets shifted up to here. But there's one other thing. This negative on my x. What it's doing is it's flipping the graph horizontally. So the graph that normally would have been going like this is going to flip over to here and have that same basic shape, but on this side of the asymptote. So get rid of it over here because that's not actually part of the graph. And there we have it. Next up, log base b of x plus 2 plus 1. Now one thing I want to mention about this. The base is really arbitrary when we are doing graphs of logarithms. And most of the time, the graphs that you're going to be working with won't include horizontal and vertical flips. They'll really only contain just horizontal shifts, vertical shifts, which makes it a little bit easier. So for instance, like here, this plus 2 is going to be a horizontal shift. It's going to move me to the left 2 units. This plus 1 is a vertical shift. And it's going to move me up 1 unit. So normally my point that I'm passing through here is there. It's going up 1 unit. And if there's no horizontal or vertical flips, I just put my standard looking graph in here. So there we have it. In terms of domain, I mentioned the domain, how that would work. In this example, if you take your argument, set it greater than 0, and solve, well, one thing you would do is divide both sides by a negative, which requires you to flip the sign. So your domain here is x is less than 0, which makes a lot of sense because that would be this set right here. And then the domain of this one, if you take x plus 2 and set it greater than 0, it's only the argument that matters, then you're saying x must be greater than negative 2. And if that's the case, that is makes perfect sense because here's my set, matches up perfectly with my graph. All right, one last example with graphing. We want to determine a function which has the following graph. Now this sounds difficult to start with, but it's generally pretty easy. So we have the basic function that looks kind of like this. The base is arbitrary. It doesn't matter what you put the base as. I'm just going to leave it as b, and if you're doing one of these with the homework, it'll probably tell you what base to use. Now, one thing that you need to determine here is what h and k are. So h is the horizontal shift, and if you'll notice, my asymptote is 2 units to the left. And if it's 2 units to the left, then what I need here is that log base b x plus 2. So remember, it goes in the opposite direction of the sign. And the k is your vertical shift. So this point of interest right here, if you'll notice, is it 3 units down from the axis, the point where it's supposed to be. So that means I need to go down 3 units, so minus 3. Now I have a logarithm that will make this particular graph.